So finishing this problem that we were just working on, we're trying to get polynomial approximations for cos of x. Um, if we had a p of 0, so 0 degree pieces p of 0 of x would just be our first term. So if we don't have any, if our polynomial has degree 0, uh, degree 0 would be 1. If I looked at degree 1 of x, it would be 1 plus f prime of 0. Well, f prime of 0 is 0, so we'd have 1 plus 0x. So that doesn't really do anything for us. So this goes away. That doesn't give us a first degree because the leading coefficient, or yeah, the leading coefficient is 0. So what about p degree 2, p of 2 of x? Well, we'd have 1 because that's 1. That part's 0, and then we'd look over here. So plus f double prime of 0 is negative 1. So negative 1 over 2x squared, which simplifies to 1 minus 1 over 2x squared. P of 3, well, P of 3, I'm going to get a 0 again. So that's going to make that 0. So that doesn't work. So we can just skip ahead. P of 4 of x would be 1 minus 1 half x squared plus, well, the fourth derivative, since it's 4, we look at the fourth derivative, which is 1 over 4 factorial, so 4 factorial, times, since it's fourth degree, x to the 4. And x to the fifth, if we looked at p of 5, p of 5 also isn't going to exist because the derivative there is 0. So we could jump ahead to p of 6. So p of 6 of x, so our 6th degree polynomial, uh, would be 1 minus 1 half x squared plus 1 over 4 factorial x to the 4th plus, well, now we look at the 6th derivative, which is negative 1. So minus 1 over 6 factorial x to the 6th. And simplifying that a little bit, we have p of 6 of x equals 1 minus 1 half x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th. And this is just going to oscillate back and forth. The next one would be plus 1 over 8 factorial x to the 8th minus 1 over 10 factorial x to the 10, and then plus minus, increasing in the same way. So, if we wanted to look at what do those what do those approximations look like, looking at the next curve, in red we've got our cosine. In black we've got our 0 degree polynomial, our constant, which doesn't work very well, but it works a little bit. In green, we've got our 2nd degree polynomial. In blue, we have our 4th degree polynomial. And I'm running out of colors here, but in smiley faces, because it works even better, we've got our 6th degree polynomial. And again, the idea being that these polynomials approximate y equals cos x for x close to x equals 0. So in other words, in this region, those polynomials are approximating cos of x, and the higher the polynomial, the better it approximates. But we're limited. We're limited in that, we've only looked at approximating around x equals 0. To approximate around any point, so to approximate around any point x equals c, it's a very simple transition. All we need to do here is just add in a shift. So the function, our polynomial function looks exactly the same, except that instead of f of 0, we're looking at c, and then we have this, instead of x and x squared and x cubed and x to the 4th, we have to shift those powers over accordingly. So a very easy change. So let's see how that works around the function y equals ln x. If I wanted to approximate this at x equals 1, remember that the polynomial approximation is going to be f of c, well in this case f of 1, but well let's write f of 1 plus my first derivative at 1 times x minus 1 plus my second derivative at 1 over 2 factorial times x minus 1 squared. Just so you plus, you should be thinking about, well, what's the next one going to be? Plus the third derivative at 1 over 3 factorial times x minus 1 cubed plus, you should get this one, plus, well, what is it? Well, the fourth derivative of x evaluated at 1 over 4 factorial times x minus 1 to the fourth dot 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 dot. And we could keep going on with that for a while. So if we wanted to do an approximation, let's do P1 through P3. So let's find P1, P2, P3. Well, what would I do? Think about. I think you could probably figure this out now. In fact, I challenge you to pause this video and find P1, P2, P3, and then you can unpause the video and see if you're right. So the first thing, we need to find f of 1. Well, that's ln of 1, which we know is 0. And then we need to find f prime of x. Well, f prime of x is 1 over x. So f prime of 1 would be 1. And f double prime of x equals, well, negative 1 over x squared. So f double prime of 1 would be negative 1. And now we're going to start getting this plus, negative, plus, negative, plus, negative going on again. Actually, no, we won't. Sorry about that. I'm going to rewrite this as negative x to the negative 2. That's going to help me take the derivative. So f triple prime of x is going to equal 2x to the negative 3. And so f triple prime of 1 is going to equal 2. So, okay, sorry, I was doubting myself for a second, but pretty sure I'm right there. So we have our first derivative, 1 over x, evaluated at 1 is 1. Second derivative is negative x to the negative 2, evaluated at 1 is negative 1. Then that negative 2 is dropping down. So we get 2x to the negative 3 is our third derivative, evaluated at 1 is 2. Okay, so p of 1 is going to be equal to that f of 1, well, f of 1 is 0, plus f prime of 1 is 1 times x minus 1. That's p of 1. P of 2 will equal all of that plus this additional component. So f double prime of 1 is negative 1, so plus negative 1 over 2 factorial times x minus 1 squared. And p of 3 is going to equal all of that, so I can get rid of this 0. 1 times x minus 1, and instead of plus, so minus x minus 1 squared over 2 factorial. That's just p sub 2. And then I need to add this last little section. So f triple prime of 1 is 2. So we have plus 2 over 3 factorial x minus 1 cubed. And so there's my third, my polynomial approximation of degree 3. So I've got degree 1, 2, and 3. And they're approximations that are centered around x equals 1 of my function ln x. And if we want to look at what those look like, you know, here we have ln x and our first degree approximation. It's decent. And on the next one, again, we have ln x. And now we have our second degree approximation. It's getting better. And ln x and our third degree approximation. And then here's a graph of the fourth, but we didn't find that. You can find that. You know how to do that. So the idea is to generalize it around x equals c, and where c could equal 0. So this works. This is the general equation. Around x equals c, f of x can be approximated by p sub n of x, where p sub n of x equals f of c plus f prime of c x plus f double prime, ooh, hold on, times x minus c plus, let me just start a whole other line because it's, you know, a little bit of writing here. So plus f double prime of c times x minus c squared all over 2 factorial plus f triple prime of c times x minus c cubed all over 3 factorial plus, I'll extend it just for 2 more of these, f to the fourth derivative of c times x minus c to the fourth all over 4 factorial plus the fifth derivative at c times x minus c to the fifth all over 5 factorial plus dot, 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 dot. And it goes on and on and on and on. And the idea being we want to approximate functions with with a polynomial because eventually what we're leading to, these will be infinitely easier for us to integrate. And that's the whole point. Okay, thanks.